if we didn't have extinction, problems could arise. That's the kind of a situation. This is actual photograph, right? Okay. All right. So geology, and if we have the appearance of a first appearance of some species, they start slow. It's really hard to see the first one. You're not going to see the first species. Extinction of a single species, a line like that, is not going to be a sudden thing unless there's a catastrophe. But a mass extinction or a extinction of a line like that is going to be easy to use, and geologists utilize these things. If you knock over those wires,
they're seeing.
Don't worry about it.
Says got it, but I don't see it on.
Okay, watch your fingers. Okay, we use extinction. They're very important for what we call biostratigraphy, using fossils to age date things. You know, I don't know what you did, but it won't advance for me. Okay, wait a minute.
They'll work.
Wait a minute. Okay. Okay, let me get started here. The eras Paleozoic, Mesozoic, Cenozoic, they are punctuated and they're recognized by extinctions. When a group disappears, something else comes out after. Easy to spot these things. My dullest grad student could grasp this idea and also could make this happen. In a larger sense, finer sense, most of the geologic time periods in the Paleozoic, Mesozoic, even the Cenozoic, are bounded or actually defined by extinctions originally. Now we define them with absolute time. Okay, but we only have 5 major extinctions. I'll show you, there's a whole lot, maybe 20 or so of these things are common, but there's 5 major extinctions and about a score of minor extinctions. So we look at the fossil record here, Paleozoic on the left, the boundary between the Paleozoic and the Mesozoic here. Each bump in here is a group of animals, a number of animals that went extinct. So we see a major extinction here at the end of the Cretaceous. We see a major extinction here at the end of the Paleozoic, the Permo-Triassic. And then all these little things on here are major or smaller extinctions. A lot of these things. And if you start looking, a lot of them come right on the boundary, like between Carboniferous and Permian or something like that. We defined these things originally by biologic extinctions of fossil animals. Okay, we recognize in the fossil record 3 major invertebrate populations. We have one over here in the lower part of the Paleozoic called the Cambrian fauna, but not only in the Cambrian, they're a little bit in the Precambrian, they're in the Ordovician, Silurian, Devonian. In fact, we have a few Cambrian animals from that time or groups from that time clear out here in the modern fauna. Okay, so we have Cambrian fauna. Then there's a Paleozoic fauna here in that ugly green color, trilobites and so forth, but they go up, they almost become extinct here at the end of the Permo-Triassic about 250 million years ago. And then the rest of the stuff, which actually started out back here at the same time the Cambrian started, we get what we call the modern fauna. These are just invertebrates. Cambrian fauna, Paleozoic fauna, and the modern fauna. And then these things are being affected by the tectonics. All right, if we look at the Cambrian fauna, it reaches the apex at apogee here in the late Cambrian. You can see it's pretty high up in here, up in there, and then it trails out and it virtually almost disappears at the Permo-Triassic, but it does continue out. There are a few Cambrian-like forms, and I'll show you a couple. Actually, this is a modern, this is a fossil lingula, and that's a modern lingula still alive. Quite incredible. We don't have any more trilobites, but most of them have died out. But the Cambrian fauna is really easy to recognize. All right, if we look at a kind of a diorama of these things, most of them are gone. Some of them would be sponges. We have crab-like trilobites here. This is a big, about a meter long predator with big mouthpiece and so forth, eyes on stuff, really quite remarkable. Again, the jellyfish of jellyfish, a few of these things are still around, but not many. Okay, if we look at the Paleozoic fauna, a little more familiar. We have crinoids in here. We have brachiopods. Both of those are still living. Not too many crinoids, certainly not too many brachiopods, but there are extant species of these things. We have horn corals. We don't have ammonites, but we certainly have nautiloids. We have some kind of a cephalopod. Anyway, they are going along after the Cambrian, and then they take this huge hit, a very big hit here at the end of what the Permian, or what we call the Permo-Triassic boundary, when about 95% of the species on this earth were extinguished, a real massive extinction there. All right, and if you look at these things in a diorama, most of these turkeys are on life support. They're still around. This would be a ancient one, but we know we have, this is an ammonite. We know we have cephalopods. We don't have any straight cephalopods. We do have crinoids. They're one or two little families of crinoids, but they're not. As I said, they're way past their sell-by date. You can tell they're ancient. They don't look at all. All right, then we get into the modern fauna, which again has been here since the beginning of a little before the beginning of the Cambrian. It goes clear back in here, starts out slow and then begins to build up. It takes a little bit of a hit here, a bump, a little bit of an extinction here at the end of the Permo-Triassic, but it includes mollusks like the pelecypod on the left, echinoderms, sea urchins on top, fish down here, crabs and snails, things of that nature. They run up to a present high of about 600 families. Again, this is what we're dealing with, most of what we're dealing with in the fossil record today, or in the excellent record. If you had to say, if you define success, when you define whatever that is, you define success, I would define success by biomass. What is the weight of animals? If there's huge weights of these things, their biomass is high, that's success. If you define it by diversity, the number of species, that's another way. A lot of different species of each end of each genus. That would be successful in my mind. And the other thing would be successful if you undergo extreme adaptive convergence. In other words, you modified yourself as a predator, as all kinds of different things. You've insinuated your way into these different lifestyles. You have a lot of adaptive divergence. And in that term, I would say there's no contest. The bony fish, the teleosts, and the snails are the most successful, at least in the invertebrate group, because of their diversity, biomass, and adaptive divergence. I've never seen, I don't know if they have such a thing as a predatory clam, but we're talking about mainly snails are successful in that way. Okay, so we talked about, we'll talk about this in detail. The end of the Cretaceous, the dinosaurs died. And the animals take modern fauna takes a pretty good hit there. Everything takes a big hit here at the end of the Permo-Triassic. Again, 95% of the species. What?
Take that off the screen.
Okay.
The bar.
I can't hear you. What?
That's all right, just keep going.
Thanks. Okay. All right. It turns out that of the 5 major extinctions we have at the end of the Ordovician, the geologic record tells us we probably had extreme global cooling, what they've called ice ball Earth or something like that. In the late Devonian, the extinction there seems to be a colder Earth and a diminished amount of oxygen. That's what their interpretation, not a meteor or anything like that. Then we know what this one is in the Permo-Triassic at the end of the Permian, the Siberian traps. It's a volcanic scenario in Upper Siberia, the Siberian traps, and that was a deadly one. We also have one here at the end of Triassic, at the boundary of the Triassic, which is a pH change, chemical change in the oceans. And then finally, we get this one everybody's talking about now, the bolide, the demise of the dinosaur by some kind of a meteor hit or something like that. 5 of these things, but only one right now has been definitely laid to some kind of an extraterrestrial event like that. All right, if we go back, go to plate tectonics, or if you wish, continental drift. The continental drift or plate tectonics dogma says that if you go back in 1 billion years ago, you start out over 1 billion years ago in a supercontinent, which we call Rodinia, which is an old name for Russia. And then later that this thing comes apart and then goes back together again. And second time around, we call it Pangea, but they don't go together the same way. If you look down here, Africa is going to be stuck into South America, yes, but North America here is clear up above on that. So they don't go there, they break apart, they go back together again, they break apart a second time. Now they're at maximum dispersal, but they didn't go back together for Pangea quite the same way when they reassemble these things. All right, so if you start looking at this, you start down here with Rodinia over 1 billion years ago, and it begins to break up. This is just a continent. The Earth would be out here. It's a supercontinent, begins to break up, and we call this one down here Gondwana. Then we have get names for these things, and they break up, and then as fast as they break up, they start suturing themselves back together again, okay? Like you're unbuttoning and you're buttoning back up again. So they break up, they start suturing back together again, and then as they go back together again, they finally wind up, you go from Rodinia, it breaks up, reassembles itself into Pangea. But when it reassembles itself, those wiggly lines are mountain ranges, ancient mountain ranges. You can see the scar tissues from plate tectonic for these reassembly. Let's see. Okay, when we go through this expansion, contraction, expansion, now we're at maximum expansion out here. We have one that one wiggly line is there where India has slammed back into Asia when Pangea was reassembled. The whole thing, expansion, contraction, expansion, is called a Wilson cycle after a man named Tuzo Wilson, who worked a lot of this business out with plate tectonics. 9, if you look at the Earth's history, we're supposed to be 4.5 billion years old. There is room for 9 Wilson cycles. This could have happened 9 different times. Well, we're tracing these things with fossils. We don't get much of a fossil record when it's older than 1 billion years, but that's the way we do it. All right, we also find that when this thing begins to break up like this, we have one continental shelf. This is the big continent here. One continental shelf in here is all there is on the outside. But when we break it up in pieces, we got continental shelves here. All this has new continental shelves. That means that the diversity is going to increase like crazy. The diversity is increasing there because these continents are breaking up. All right. Then when they put themselves back together again, the diversity goes back down again. Diversity, number of species, genera goes up, and then it puts it back together, back down again. And then again, now we're at maximum diversity. This diversity line is going up and increases again, going back and forth like a breathing lung. All right. This is a man, David Jablonski, is co-worker Sapkowski is passed by now, but they made an extinction, they made an amazing discovery, wrote a neat paper in Science called assembly line extinction and its edge effect. And I'll show you how it works. He's at the University of Chicago. It's really brilliant to see this thing. You see something like the work they've done and you're kind of envious. I mean, I'm not afraid to admit that, but these guys are really incredible vision, all right? what they discovered was that the edge effect, organisms, when they die, communities of organisms, they start out in shallow water. You can think of the shallow water up in the surf as a kind of a crucible of evolution. That's where new species appear. And slowly they boogaloo across, do you get that verb? They boogaloo across the continental shelf. They get out here to the edge of the shelf, and you have the slope out here. The water's cold. There's not that much oxygen. It is at the edge of the shelf, and that's just where I see it's changed. This is a slope here. They have extinction out here. So the organisms, and the general pattern is that as they appear for the first time in the upper shelf areas in the surf zone, rich in oxygen, lots of nutrients, sunlight, you got a whole system working there. They migrate across the shelf, not over a week, but over millions of years, and they get out here on the edge of the slope. This is where they do extinction out in there. We call that's the edge effect, and it is a similar line of extinction. Now, if you look at the actual geologic record, it looks like this. What we're plotting here, across the top, we're plotting depth. This is a shelf zone in the middle shelf. You can see up at the top there, the continental top of the continental shelf. The continental shelf moves down. You get to the edge of the shelf, and the slopes are here. So new organisms are going to appear in the surf zone, and then slowly move across there to become extension. When you have, let's say, we got a range of animals here. Each little colored bar is not an individual. It's a community, not a population, but a community of several. It's got predators, it's got scavengers, and so forth. And they first appear down here. This one appears in the Cambrian, this yellow one. And his range, he starts here, and he's extinguished here. That's as far as they go right there. That's when the last one croaks, right there. Okay, so the range of this yellow community, which you can actually follow in the fossil record, if you're as thorough as Dr. Jablonski, you can see the range of these things. Look what they're doing. They're moving from shallow water steadily out like that, and then they become extinct. Okay, mass migration, again, it's over millions of years. They're going. It starts out in the Cambrian, wherever it is, your Cambrian here. And they don't become extinct until well into the Ordovician, several millions of years. Okay, we have several examples. The other one I have here is just the purple one here. He starts out here at about 490 MYBP, million years before the present. And then again, they do the same thing. They bebop right out to the edge of the shelf. And then the last one is up there. So its range goes up to here. Two different communities, and not looking at individual species, but we're looking at mass extinctions, slow, or what we call assembly line mass extinctions. So we can say, again, new species appear in the surf zone, which is a high energy, well oxygenated, nutrient rich zone with a lot of light, by the way, in the shallow oxygen, nutrient rich water. That's the crucible of evolution. And then the outer shelf and the upper slope is where extinction takes place. At least this is for the benthonic or bottom dwelling organisms. They appear, I guess I just repeat that. All right, if the inner shelf is turbulent, oxygen rich, nutrient rich, and plenty of light, then the converse of that, and the outer shelf, the water is extremely cold. Sometimes they're freezing. The oxygen is depleted, and there's no light. So that's where they go extinct. Actually, the question you should say, why do they migrate? The thing that Jablonski said is that you have competition for the next group back is pushing you out there, competition. That was his notion. Assembly line extinction and of bottom dwelling communities. Okay, so we say, interesting, we want to look then at what I said, folks that didn't get the message, animals that kind of lasted. And we're going to talk about these or just list them from the youngest to the oldest. Normally in geology, you start with the oldest and you go to the youngest. In this case, I went from the youngest to the oldest. And these are what I call the winners. These are the ones that lasted a long time. And most of these you'll recognize. And it's been my experience that you can learn a lot more from winners than from losers, okay? The losers went extinct, all right? So if you look at some of these things, everybody's familiar with this. And this is a version of it that's on the Capitol grounds there in Salem. And then there's a modern leaf up there that was brought here from China in 1926. But again, I see the dates are not on there. 14 million years ago back. And then the fossils of these things unquestionably Metasequoia. It is no doubt that it's the same taxa. Another one that goes back, let's say, about 70 million years is a Cretaceous pelecypod clam, and it has a kind of a dentition that's nothing quite like it. I know it. If I was dead, I would know this thing. I would reach from the grave and identify it. Okay, it's called Trigonia because it has kind of a triangular shape, but the dentition here is very, very distinctive. These are fossils. This is the one I'm interested in here. All these three here are fossils, but this is one that they found living in the Great Barrier Reef, kind of like a Nazi in Argentina or something like that. That was a joke. Okay. All right, so we've got a clam here that's still hanging on. Then again, when this guy was found, and that's definitely Trigonia. There's too many details that are the same, not the same species. But the people who do mollusks, I remember I was absolutely astounded by this discovery of a living fossil in the Great Barrier Reef of Australia. Another one, which I see a lot of out where I am in Northern Marion County, along with skunks and opossums, and raccoons, is opossums. You look at the skeleton of some of these opossums, it's incredible. You look at a Cretaceous one, you look at a modern one, they're extremely close. They are about as primitive a mammal as you're ever going to see. It is not a reptile, although it looks like one. But it is incredibly primitive. This was actually a placental, but it's an amazingly primitive organism. And he's been around in one form or another since the Cretaceous. Another favorite of mine, going back 140 million years, really slow, real Republican, slow evolution, very conservative. The crocodilians, there's a whole groups of them now, they're fairly successful still. They go back to the Jurassic, but again, as you know, they're living today, living fossils, all right? Another one is the Araucaria. We have one of these in the place. The fossil and the modern ones are absolutely identical. It's called a monkey puzzle tree. They go back to we're going back in time, 180 million years to the Jurassic. We go into a couple of 100 million years, a fifth of a billion years. Tuatara is literally a breed. He's alive today, but the ones in 200 million years, fossils are identical. They're just for all intents and purposes. We don't have the liver, guts, and gall and skin, but that's good enough. The bones are pretty persuasive. As a living, breathing fossil, Tuatara. It's just a little thing. Most of you are familiar with Limulus, the horseshoe crab, which goes back and 230, almost a quarter of a billion years, 230 million years. Okay. Got those on the East Coast. Ginkgo trees, now we are at a quarter of a billion years ago. Ginkgo trees, some modern forms. I have one growing on my farm, and in a fossil form, the Ginkgo biloba, it's just the same, very same. You start comparing the xylem of the plant, all the details, they all match up. It is truly a living fossil. Another one is Calamites, or there's a specimen here from the Mason Creek locality in, I think, Illinois, maybe. I can't remember the state. Again, it goes back to almost a third of a million years, a third of a billion years. Calamites, a scouring rush. Getting back now to definitely to a third of a billion years. Cockroaches, a modern one here. The one on the left is huge, 6 or 7 inches in size. But they, for all intents and purposes, the details are there. It's still going on. You go back, we're at 330 million years. The Pisna silverfish, you have those in your house. These are a living fossil too. They're perfectly preserved in some of these Paleozoic intervals. And it's the same, for my money, it's the same taxon. Okay, we get to 400 million years back. Most of you have heard about the Latimeria, which was discovered off South America in a couple of thousand feet of water, at a deep. 1939. That's the year I was born, but I'm not that old. In any case, he's still around. They have these things, they're live, they do have everything. The ones, all the intros, it's illegal to catch them now. It's a very primitive lungfish, but he goes back almost a cool 400 million years. Then you get to this guy, it's a snail, like a snail, and you can see the muscle scars on this fossil. Here's a modern one over here. This is one that when they found a modern one, they showed this guy that studied these things his whole lifetime. He practically grasped his heart and checked out. He was so amazed, and he just couldn't believe it. And they showed him a real one. Inside, the muscle scars all match, and I'm pretty sure that's the real thing. You're getting back now almost 500 million years in time. You still have players there. We already showed you a lingula. This is our modern one. These are fossils. That's a fossil over there. Look just the same. And actually, they apparently have exactly the same habitat, a shallow, muddy ocean bottom. Lingula, a little over 500 million years. You getting tired? We're stopping here. This organism, Peripetus, was first described. Well, this is a fossil described from the Burgess Shale, which is Middle Cambrian, and this guy is older than that. And then we have these are modern ones here. It's still going strong, identical, and in every detail we can see in both the fossil and modern part, they match up perfectly. Pretty impressive. There's something about these organisms that they got through and everything else went extinct. All right, so for the benefit of the motorheads, does anybody here work on cars? I do. For the benefit of the motorheads, we get another example of that in this 1937 Volkswagen. This is kind of neat. It's got no bumpers. It's got no rear view mirror, no rear window. It's got no rear view mirrors. It has suicide doors, and it has these cool levers up the back, but it's a Volkswagen. It doesn't change much. What? Baffles? That's where the motor is. It's to keep the thing, heat is a big problem. It's air cooled. But inside, they look pretty much like a modern Volkswagen. My father bought one in 1955. We've had them off and on. They're not making them in this country anymore. They're making them in Mexico. I think they're still manufacturing them, the old Beetle type things, and they're manufacturing them in Brazil. So they haven't gone extinct. But that's a long run for a car. Okay, let's go back to the extinctions. I said we had 2 mass extinctions, really big extinctions. Here, one is the Permo-Triassic Indo-Permian, when we lost 95% of the living organisms on this earth. That's plants and animals. And the other one is here at the end of the Cretaceous, 66 million years somewhere, where among other things, the dinosaurs and a lot of other things died at that time. We use those 2 boundaries to define the Paleozoic, Mesozoic, and Cenozoic. They marked the boundary. Originally, they marked the boundary, and they were defined in that way. When the Siberian traps, which are responsible for the Permo-Triassic disaster, was firmly inside of Russia, and we had to wait till the end of the Cold War to get in there. It was really a gold rush. Everybody wanted to get in there and see these things. The extent of the Siberian Trench, just like the Columbia River basalts, are huge in extent. And there's pretty good evidence that when they erupted, they not only corrupted the air, and it's a basalt, it corrupted the air, but they also corrupted the chemistry of the oceans themselves. So everybody kind of took a hit there. A few things survived. This is a picture with the outcrop. They're really well worn because this is an old unit. It changed the atmospheric and oceanic chemistry both and caused a major, major mass extinction. All right, then we have here David Raup, who was Jablonski and Sapkowski's major professor at the University of Chicago. And he says the Permo-Triassic, that's the one, Permo-Triassic is 95% of the species on and marine taxa. He says as close to total annihilation as we've ever come. Nothing's even near that. But he said the most amazing thing to him was how rapidly after the event, the Triassic fauna has recovered and began to move on with their life. They regrouped and they continued on to Triassic. All right, so let's talk about dinosaurs. I think this is a Larson cartoon. That's not my persuasion, but another maybe something like this if you're religious. He finally got the laugh track on. I see that. All right, so this fair guy is a Canadian, Digby McLaren, professor in Canada. And way before they found evidence for meteors, back in the early 1960s, McLaren just got this idea popped into his head, and he wrote a paper which said that mass extinctions, and he was talking about the Cretaceous and also the Permo-Triassic, are caused by what they call bolides or meteors. Okay, he just wrote this paper. Okay, no physical evidence whatsoever. Didn't have a thing, not a shred of evidence. And he wrote the paper, and everybody thought he was either a seer or he should be institutionalized somewhere quietly. But he came up with the idea. When he published this, the idea was immediately popular, but with no evidence, the paleontologists sort of sat on it. There was nothing to work with. It didn't offer anything. So the paleontologists were rather slow to accept that. Then later in the 19, let's see, I can't remember the date even, but this was the Alvarez team, the father, his son, 4 people in the team. They worked on the Cretaceous. They found this iridium spike at the end of the Cretaceous, which we think was due to a meteorite. But and then immediately they said, well, let's kill the dinosaurs. This is what killed the dinosaurs. But none of their people, I don't think it even take it. Well, he is a geologist. The others weren't, and none of them are paleontologists. They had no idea about life cycles or lifestyles at all. Nevertheless, the notion of a meteorite was a really big hit immediately, particularly with the media. They loved it, and they began making drawings like this all over the thing. It was only been in the last few years that they realized that this thing would set off gigantic tsunamis. It had to, but we're seeing the evidence for that now, for tsunamis. The hype was pretty serious, and the paleontology community that I belong to was not too happy with it because they weren't appealing to any paleontology evidence at all. At that time, I was working for the federal government, giving your money away to geologists that were paleontologists. I was the program officer for the National Science Foundation, and I had a budget of several $1 million. And I had a committee, and we doled money out to people who wrote proposals. Everybody had a proposal. Some of them weren't too good because it was really a fad that went on. All right, then it all they came to loggerheads, and for a long time, the papers listened to the Alvarez gang. And then finally, some of our people, and this guy, if you don't ever seen Bob Bacher, he's something else. He's a very bright guy, but he's not anybody you want to go up against verbally or physically. He's a big guy and as smart as can be. He said, let's just stop for a minute. Wait a minute. Let's look at the geologic record. Let's kind of slow down, look at the geologic record. And he said, if you look at the moon, that's what it looks like today, it is absolutely pockmarked with meteor craters. And it is way smaller than the Earth, very, very much smaller than the Earth. And yet it's been getting hit by meteors since eternity. So there should be meteor craters everywhere. And he said, we start looking on Earth. This is one in Canada, Manakougan. These are meteor craters. One in Arizona, most of you know about that one in Arizona. Here's one in Bavaria where they built a little community. That's the rim of the crater there in Bavaria. At least that's how it's been interpreted.
Actually, that one's about 20 miles apart. That's just big.
Okay.
It's round because that's a medieval wall.
They built the wall. They built the wall on the berm. Okay, this is one in Alice Springs, Australia, and so we have a few meteor craters, but the Earth, unlike the moon, has the capacity to erase these meteor craters by 3 strategies. It can do it by erosion. You can erode these things away, and they are being eroded away. You can deposit something on top. You know, if you make a cake and you make a mess of it, you can put a lot of fudge like chocolate on top and hide your crimes underneath that. You can bury your problems that way, and people are even happier because there's more sugar. Or in the ocean, which is most of the Earth, we had this process called subduction. We're recycling the ocean. If you go past about 200 million years, you've recycled, the oceans are completely recycled. The moon doesn't have any of these to speak of. Doesn't have an atmosphere, which would slow down some meteors. But as I said, that it carries all of mine. This is just a complete record of meteor strikes. And that's his point. All right, so then he said, what we've been saying all along was that the extinction of dinosaurs was probably due to a volcanic event. And the candidate event, which was 66 million years ago, is called the Cretaceous Tertiary, the KT boundary. And it's called the Deccan, DECCA. I know it's chopped off there. This is in India, the Deccan Traps, okay? The huge eruption of volcanic basalt in the western side of India. So if you look at India, this is where the Deccan Traps are on the western side. It starts down here. This is Reunion Island. That's where these things started. So India was part of, it broke loose from, according to plate tectonics dogma, it broke loose from the South Pole, and it starts kind of boogieing up here this way, comes up, and it passes over Reunion Island just about 66 million years ago, gets this huge imprint. It keeps going, and then this develops, a spreading center develops here, pops, it goes up in here. So the Deccan Traps are here, but they were erupted down here, all right? And they're huge if you go there. It is a fantastic volcanic edifice. This is what Reunion Island looks like today, kind of innocent looking, but then when that passed, this is a hot spot. This is a mantle plume. When it passed over that thing, there's pretty good evidence that caused the Deccan Traps. So the message was taken on and attached to Asia, all right? But what I said here is the Cretaceous extinction is not only about dinosaurs. These are rudisted clams. It's a clam that's kind of having an identity crisis because it thinks it might be a coral or something. It's got a lid on top and it's a filter feeder. But look at these things. We have these in the Cretaceous, zillions of these things, huge a number of these things. And they disappeared at the end of the Cretaceous. So in fact, the dinosaurs, by comparison, were just a sideshow. These are, I worry about this. Dinosaurs, no big deal. But the loss of those clams, the biomass there is almost unbelievable. Other animals, as I said, that didn't make the Cretaceous chop were several groups of planktonic foraminifera protist on the outside of pelagic plants, microscopic plants. The ammonites didn't get past that, and the belemnites. Now they have cousins. There's a squid, and they have a cousin here, which is kind of a distant cousin, the cephalopods, but none of these got through it. But these are pretty big populations too. In fact, equally, certainly the foraminifera and the calculus and so forth would match what they had in the picture I just showed you of the redisted clams. These didn't make it, okay? In the marine reptiles, we have the mosasaurs here, which is a sort of a crocodile on steroids. And we have a pliosaur, which is the same way, a different group. The ichthyosaurs, which is a reptile that thinks it's a porpoise, I think. And then we have the plesiae. These are all reptiles, but they didn't make the cut. But they all disappeared at different times, not quite the same time. Cretaceous reptiles took a pretty bad hit. Interestingly enough, we have 4 groups of reptiles: the turtles, the lizards, the crocodiles, and the snakes that did get past the interval, something they had. These are the winners. The reptiles, the dinosaurs were the losers. Okay, these organisms survived the terminal Cretaceous event. All right, so then we go back to Dr. McLaren, and he looks at this and he says, you know what? And then still didn't have any evidence, but he says he decided that all mass extinctions, you saw they had over 20, they had a score of these things. So we first started talking to you. He said, these are all due to bolides. Every one of them are all due to meteors. He just says blanket. He published a paper, which was a bad mistake, because after that time, a few years later, Gerda Keller, a Swiss geologist, she began to look in detail at the record, and she discovered that most of these Cretaceous forms began to kind of attenuate or thin down before the extinction. Yes, they were dead by the end of the Cretaceous, but not at the end of the Cretaceous. You could say by the end of the Cretaceous, they were all gone. That's not the way a meteor works, okay? Unless it really changes this thing. And all these things, they seem to began to attenuate, and they disappeared. Some of them were well before the end of the Cretaceous, but they were a Cretaceous form, which by the end of the Cretaceous was gone. So they got kind of lumped together. So she is in favor of some kind of a gradual process. The bolide people, when they saw Dr. Keller's evidence, they want to save that. You can't help yourself if in science. You want to save your idea. So they said, well, why can't we merge those two? Why can't we have a meteor strike the Earth and cause volcanic activity? And the reason you can't, I wouldn't think you could do that. Problem with that is a bolide, a meteor, is a top-down process. It's coming in from outer space. These mantle plumes, they start down almost 2,000 miles in the Earth and come up from the bottom, okay? It's bottom up, others is top down. So it's kind of hard to marry those two and to get set to work as a process. Mantle plumes are a really big hot item right now. We have a mantle plume a little bit to the east of us, which used to be right on the southeast corner of the state at the McDermott crater, and that's Yellowstone, and it's still an active volcano. We have one over to the west of us a ways in the middle of the ocean, Pacific Ocean, which is Hawaii, which is another mantle plume, which is kind of raising hell right now. But the model, if you know what a lava lamp looks like, that's not a good model, but it's a fair model for these mantle plumes. They're enormous structures. The average age of a volcano, one of these composite volcanoes in the Cascades, is about 1 million years, give or take, okay? Not always, a little bit more, a little bit less, around 1 million years. But these mantle plumes, they go for hundreds or millions of years. They're just like a nasty, infected, separating wound. It's always breaking out. It's a real problem. So these things are a long-term thing, a mantle plume. All right. All right, the other thing we look for a lot in geology is cyclicity. I have two of my students in the room, believe it or not, he took classes from me. Another is in the back who was so kind as to drive us here, Sheila. And they'll tell you that. I always tell them, if it happened once, if it happens, it happened before and it's going to happen later. Everything's kind of cyclical. It may not be exact, but cycles are what geology, particularly paleontology, is all right. We have what we call the holy grail of paleontology, is to find some kind of a repeating geologic, like a mass extinction, a catastrophe that we can match at regular intervals with extinctions, okay? We can match those two. We can say, well, whenever we have this happening, we're going to have a mass extinction. Cyclicity, all right? So we go back again to the University of Chicago. Here's Dr. Sapkowski, died young. He's also gone. Dr. Raup, and the three of those guys, mainly Sapkowski and Raup, came up with what they call the nemesis idea. I know you can't read it there. Was a creative idea that went, as I said, it literally went bad on them. What they said was every few millions of years, you get mass extinction here in the geological. They're going back to 250. That's Permian to the. It just go back to Permian to the recent. They say every 30 million years or so, we get this mass extinction. And they said they think it was a celestial thing from outer space. They said what it was a what they call a binary star, where we have our sun, and when our sun is where we're rotating out here, when these things are spread apart like this, I got it wrong. It's spread apart like this. We're way far away from both the suns, and we have normal times. But when these things, two binary stars overlap, and for a period of time, they're close to both these suns, that's when you get mass extinction. Okay, that was their idea. And that was called the orbit of Nemesis. That was they started looking for this thing. They looked for a long time. They never could find a candidate star. Then the disaster occurred. And that was when the newspapers in Chicago saw this, that these guys were working on this thing, Nemesis idea. They named the Nemesis star the Death Star. And boy, Dr. Raup didn't die for another 5 years, but I bet he nearly died at that. He was mortified. I've never seen him so upset because they picked this Death Star thing up and kind of mocked him. And man took himself pretty seriously. And he was certainly, he was an able paleontologist. Okay, so on a lighter note, anybody here was an OMSI camper? Was anybody an OMSI camper? You know what they are? OMSI, he was, okay? You'll appreciate this. The rest of you guys, get the hell out of here. Now, this guy knows. He was an OMSI camper. He would go over to Camp Hancock under, did you know, what's the name of the guy? Well, Hancock, Dr. Han. Yeah, I knew him shortly. All right, Dale Russell was a NAMSI camper. He was for a while, he was at the Alberta Museum in Canada. He's currently, if he's still alive, he's at the head of the Department of Geology in South Carolina. And Russell said, you know, he's talking about extinction. He said, what if the dinosaurs did not croak at the end? Not all the dinosaurs croaked, but maybe some of them, instead of dying, they evolved into a bipedal reptile. You know, there's a lot of reptiles that can walk like we do. I don't know if you know that or not, and they can handle things. But he said, what if it evolved into a bipedal reptile like the primates, a hominid-like organism? Okay, so he got busy and he made one. Okay, Dinosaur Man. It's in a kind of a glass casket-like thing. One of my female grad students said, I had a blind date with that guy one time. So it was a total disaster. Okay, it was amazing. If you see this thing, it's incredible. Much more. Everybody said, the parents would say, we're going to see the dinosaur. The hell with a dinosaur. We want to see the dinosaur man. They wanted to see the real thing. And they had one here like it was real, although they portrayed this thing. Very clever idea. His candidate for the predecessor or the progenitor for dinosaur man was a thing called Trudon, which was a bipedal dinosaur about the size. It is a predator. This would be he said, if it had evolved, this would have been the parent of dinosaur eventually after a lot of evolutionary changes. And he had both these things. When you walk inside the museum, you can see a mock-up of Trudor and also Dinosaur Man. What Trudor has, he has on his limb here, it's like a thumb. It's opposed. That's actually like a thumb. He can manipulate with this thing. As I said, it's about the size of a velociraptor if you saw Jurassic Park. Extremely, it was imaginary, but extremely creative and incredibly creative. Thanks for your attention. You should ask yourself, does this man believe that, do I believe that the end of the Cretaceous was due to a meteorite or to an eruption like the Deccan Traps? And I should have an opinion because I was giving your money away to people. You can't give it because they don't believe it. In fact, you should give it to people who don't believe it. For a long time, I resisted the idea, but then a lot of other evidence has come in. I don't know how you can adapt all these pre-extinction demises that came up. They can show that these things began to, as I said, kind of wane or attenuate and then die. But we start seeing evidence now. Right now, I told you the hot thing is these. They had these monstrous. They estimate some of the tsunamis may have been as high as a mile, which I can't even get my mind around that. But I've sort of come around, and I'm not firmly a believer yet. But I think that it's you think about. I think about it a lot. I really haven't made up my mind. And this took place back in 1978 when the discovery of that the Alvarez's made with the dinosaur. So, and right now, I would say in my community and the American geologists, I would say there's still maybe 30% who doubt that it was a meteorite. They said, yes, there's evidence for a meteorite, but the other evidence, the way the animals disappeared, doesn't fit too well. But the other 60 or 70% say, no, it's just a matter of working out all the details and answering these questions. I don't think they saw a light in the sky and then died or something like that. But they began to die out. Something was happening to the environment. It was changing before that time. But the extinction of the dinosaurs and some of these mass extinctions were pretty profound. The one I showed with the radistids, when you disappear, that's a lot of biomass to get rid of. They're not very diverse, but you can tell areas I've known in the Cretaceous, you can spot the Cretaceous as radistids everywhere. Fantastic.
You got any opinions about the end Triassic extinction event? I'm kind of personally interested in it because that's what killed off the thalattosaurs and opened up the world of dinosaurs. And and I've heard that it might be due to Rangelia. Matt, the salty reference from Rangelia.
I don't know.
Oregon.
No, I'm kind of ignorant of the end of the Triassic.
So Greg, that's the extinction event that my girlfriend works on. And one of the leading ideas for that extinction is the rifting of the Atlantic Ocean and a lot of the failed rifts in the Atlantic. So the large igneous provinces, so what they call the lips. Okay, so it's the Atlantic Ocean, large igneous provinces, and not Rangelia. Right. Oh yeah, I mean, that's sort of like the dominant idea right now is that I haven't heard too much about Rangelia being tied into the extinction event. But I have heard about the largening of the Atlantic.
So did some of these sound like the meteorite would be like an instant event that had happened? the
No,
Permian?
no, well,
What were they,
no.
were they taking like
the,
million years?
they talk about a nuclear winter. But if it's anything, if it's no, it's not going to be instantaneous death for everything. It might have taken a year or two, and the whole environment changes. Yeah, I can buy that.
Geologically, that's instantaneous.
Yeah, well, that's right. You're right. In real world, it is instantaneous.
What about the other mass extinctions though? Were they instantaneous as well? Or were they over like millions of years of it?
No, not millions, not millions of years. No, if it's millions of years, that's just the vicissitudes of time. But when they show a disappearance of animals pretty rapidly, and we use them all the time. We can spot these extinctions in the geologic record. It's, you can't argue that. Other questions? Somebody else had a question.
Oh, I just had a comment. I read today that the column of hot rock about 4,000 kilometers wide is rising below the surface of Mars, indicating the planet is still developing.
Okay, now you'll have to repeat it for the 84-year-olds. Okay,
A plume, a magma plume that they're seeing in
A hot
Mars.
natural plume is rising above the surface of Mars.
what did
Below, it's rising to the surface of Mars.
I'm still not getting the question.
Oh, it's not a question, it's just a comment.
Oh, okay, well then make the comment so I can hear it.
Sorry.
Say it again, please.
Oh, sure. A column of hot rock about 4,000 kilometers wide is rising below surface of Mars, indicating the planet is still geologically active,
Yeah,
according to a
well,
study.
yeah. Actually,
Really not Mars. I know.
no, but the Yellowstone mantle plume is it's interesting because it turns out that the mantle, the reservoir is much closer to the surface than we imagined when they did geophysics. And that's one bad thing about it. And it's also way wider, much bigger. So it's capable of, they try to gauge the size of these things, the eruption that could take place by comparing it to a volcano like something in the Cascades. And it's frightening actually, but when you see they've got the ash and they got this track of volcanoes across southern Idaho, from southeast Oregon to northwest Wyoming. The ash from each one is different. It has a chemical different chemical signature, and you can find ash. You can find that ash on the east coast of the United States. In fact, it's a marker. These are markers, and they'll tell you exactly when the thing started. That's kind of frightening. The size of Yellowstone. Mauna Loa is currently erupting, but it's a basaltic show. There's not that much, it's a little bit different composition. And if you work at it and you're in Hawaii, you can get killed by a volcano, but you kind of got it takes some time. It takes and some skill or stupidity or something. It wouldn't be hard if it were a big eruption, but Mauna Loa, those kind of eruptions are comparatively benign. At the end of World War II, my father was stationed in the Hickam Field, which was right next to Pearl Harbor. So when the war was over, we went over there and we were there for 3 or 4 years. And I was absolutely riveted. We took a LST, if you know that, landing Navy ship over to the Big Island. And I was, I don't know, first or second grade, something like that. I was riveted. That's not why I went into geology. But I thought, and I remember everything. I never forgot it. It's pretty interesting, but you can get pretty close to those eruptions and they're pretty benign, but they'll survive. Yellowstone or something is going to get near silicic rocks. You get a huge number of people killed by that. They killed 54 people in the eruption of Mount St. Helens. People shouldn't have been there, but they were surprised at how big it was. It's always a big surprise. Yes.
Is it necessary to have a mantle plume that produced the Hickam traps and the Siberian volcanics you mentioned? Do they require a mantle plume?
That's the way they interpret. People who do this interpret. They interpret there's a mantle plume under Yellowstone. We first see it in the geologic record. It's in southeast Oregon. And as the plate moves over the top, it sort of burns a series of holes in the crust. But what they're asking your question is, how was it, did it come ashore and somewhere in California? And other people say, no, it was still working its way to the surface. I mean, it has, but it's active. It's quite active, Yellowstone.
But the large deposits of volcanic material like Siberian River basalts or the Siberian traps or the Deccan traps, do they require a mantle plume to create all that?
They don't, yes, that's the current wisdom of the people who do that kind of work, is that in order to get that, well, you look at the mantle plume we had under Oregon, which would be Yellowstone. It's over Yellowstone now, but it put out 50,000 cubic miles of lava. And then one of my colleagues over in Eastern Oregon said, enough lava to build a wall of lava 1 mile wide and 2 miles high around the entire Earth, which is a lot of lava. And it's a comparison. So when they start going, and it's an intermittent thing, it kind of comes and goes as it goes across. But we haven't had the big outpouring of basalt since it was in, that's from the one when it was at McDermott crater. What happens to the Columbia River lavas is that every few years, at least since I've been in this racket, they kind of annex somebody else. So the lavas, it's like a living thing. They're annexing. You think, well, this is the CRBs, because they used to be just a little bit, but now they've picked these things up and they've got it clear down into Utah and Nevada and Northern California now, whereas it used to just be confined to Oregon and Washington.
Incorporated the steams, basalts
Yeah,
into the-
pretty impressive. Well, I enjoyed it. Thanks again.